Thank you very much. Well, thanks for arranging this for me. It's really a very special place for me, and the first time I ever being at Collège de France. So today I'm going to talk about some reasoning work. Oops. I don't see the. So it's about interacting particle systems. Some fast algorithms for both classical and quantum n-body problems, and also non-convex optimization. Well, I apologize if some of you heard part of this talk, but I'm sure this quantum n-body part is quite new, actually. All right, so let me start with the classical particle system. So this is a very elementary equations. It's basically Newton's second law. So the first set of equations, I don't know why the laser doesn't work. Oh, it's here, sorry. So it's basically you have m particles, x is the position, and v is the velocity, all right? So the first equation is just definition, dx dt equals velocity, and the second equation is Newton's second law. So the left-hand side is ma, okay, assume the mass is 1, so this is acceleration. The right-hand side are the forcing terms, so you have some external force, and what's important here in my talk is this interacting force. So all the particles, every particle will interact with all the other particles. So you have all the n summation term here, all right? Well, if you take some limit, for example, over-damped limit, you have this Langevin type equations. You can eliminate the v, so you essentially get this first order particle systems. You have external potential, okay, given by some grad of some potential. And this is interacting potential between particles. And you may allow some Brownian motion term here. Well, I made a main idea and theory for these equations, but that same idea works equally well for the second order systems, all right? Of course, talking about applications is just enormous. It's basically from all walks of life, from physics, chemistry, if you do molecular dynamics, electrostatics, astrophysics, when you model stars and galaxies, all right? Those are like particles. In the last 1 or 2 decades, there's an emerging field of in biology. We use particle system to model collective behaviors of agent-based model like flocking, swarming, chemotaxis. Also in social science, for example, mean field games, Wells distribution, opinion dynamics, pedestrians, and so on. You can also model some of data science problems like clusterings as a particle system. So not to mention that the particle method is also a numerical method to solve a lot of high-dimensional PDEs, for example, kinetic equations and the mean field equations and so on. All right, so here I used the slides of Pierre-Louis Japan. Just convince you that I didn't make up this problem, okay? This is the problem that is well recognized. I mean, this here, keywords is n can be very large in all these different applications. Cosmology is easily 10 to the 20, okay? If it's dark matter, it's 10 to 60s. In plasma, it's usually 10 to 20, 10 to 25. Biology, 10 to 6 or 10 to 12. And so I mean, the keyword is n is very large, but sometimes, of course, when n is very large, you can take a so-called mean field limit at send n to infinite. The way to do that is you define empirical measure. So you basically put the Dirac mass on each particles, then take average. And you can prove if n goes to infinite under certain assumptions on the external potential and the interacting potential, then either this empirical measure or first marginal converges to this Fock-Planck equation, where this external force gives you this drift term, interacting potential gives you this non-local convolution term, okay? While the Brownian motion gives you this diffusion term. All right, so here the main question is that these are dynamic systems, but just ODEs. Everyone can solve ODE, all right? But the hard part is that, as I said, n is very large. And because of this interacting potential, you have this odd n summation for each particle. You have odd n summation, which means for each time step, you have totally odd n square summation, all right? So when n is like 10 to 20, n squared is simply, you cannot, it's too much for us to handle. So the question here is that the size of the problem is simply too much. And of course, there are a lot of classical numerical methods developed to stress this issue. I mean, n squared you cannot afford, so what you can afford usually is n log n or even order n. FFT, for example, is one of such examples. And the fast multiple method was certainly developed exactly to address this issue. Okay? When you have binary interactions between, say, Coulomb interaction between electrons. But the fast multiple method, of course, is very powerful. It's one of the top 10 algorithms of last centuries. However, it's quite a sophisticated method. And it works very well for short-range interactions. All right. But today I will introduce a method, what we call the random batch method. And that's the same work. I mean, you want to reduce cost from order n squared to order m. But it's a very simple method, extremely simple, and works for very general interaction potentials. All right, it's embarrassing simple, actually. So here is the method. Okay, joint work with Lei Li, who is a young faculty at the Shanghai JiaoTong. Jianguo Liu is, some of you know him, he's at Duke. So here is the method, just 2 lines, all right? So basically we have these particles ordered, labeled from 1 to n. So suppose we select the time step, then at each time step, you do a random reshuffling, all right? You regroup this 1 to n randomly into small groups. Or you randomly regroup them into little n groups or batches. And each batch has only little p particles. And p is much, much smaller than capital N. For example, you can even select p equals 2. It means you have n particles, randomly group them into 2 particles or each group. All right? Then the second step, each particle will only interact within its own group. They don't interact with all the other particles. You just interact within the group. So that's the method, all right? So if you write the code, it's just few lines, all right? So you select time step, and suppose you have done it m time step. What do you do next? Is that you regroup this little p times n is capital N. You regroup them into m batches randomly, okay? It's like after you play a deck of cards, a card game, you just reshuffle each time after the game is over. Reshuffle it. Then what you do is simply replace. Remember here, before we have all the n summation here. Each particle interact with all the other particles. You replace that by all the p summations. Basically, suppose you have p particles in each group, the particle only interact within its own group. Clearly, if p is very, very small, and this is order 1 summation now. For example, if you choose p equals 2, each particle only interact randomly with another particle. So this is order 1 summation. Then this whole system is order n summation, and cost of computing order n in this ODE step. All right? So the ODE step clearly is order n, but the random shuffling step is order n. Already in the 70s, there are already algorithms developed, which does this random shuffling in order n cost. For example, if you do MATLAB, you just use this subroutine called a random permutation. All right, that's order n algorithm. So therefore, the overall cost of this method is order n, as long as you choose each group is very small, order p is very small. And that other way to do it, okay, this is a random permutation, but you can do it in another way. So I have these m particles. Each time I randomly draw p particles, let them interact, then put it back. Draw another p particle, let them interact, put it back. And after you have done little n times, remember little n times p equals capital N. After you've done n times, you finish 1 time step, okay? So that's what we call the random batch with replacement. So of course, by doing this, you may miss some particles, and some particles may be drawn more than once. But here, we talk about the average expected value, so that's the same. Okay, so that's different version. Whoops. And so clearly, now the computational cost per time step is reduced by order of n. But the question is that, does it take n times longer to finish this process? Suppose you interact with n particle. Each time I only interact with 1 particle. So it looks like physically, I mean, it takes n times longer to finish this whole process, right? Whoops, what's going on? Every time I turn page, it turns off. And so therefore, it's for this method to be serve the purpose, and you have to prove essentially that time step, it does not take n times longer to finish the same physical process. You have to prove this time step must be independent of n. Otherwise, you don't gain anything, okay? And another bonus, actually, if it's Coulomb interaction, each group has two particles. Basically, each particle do Coulomb with another particle, and this step can be solved analytically, which sort of removes the stiffness, because when you have Coulomb is 1 over xi minus xj. You have singularity when the two particles are too close to each other. But if you can solve this analytically, of course, there's no stiffness. Okay, you may wonder where this idea come from. There's at least two ideas which kind of inspire this approach. One is, nowadays we know the most bustling word in scientific computing is machine learning. Everybody, all the young people, at least in China, want to do machine learning, maybe also in France. So machine learning, actually, in the end of the day, if you do, for example, deep neural network, in the end of the day, it comes to a minimization problem. Minimize a function which is non-convex, very high dimension, and a summation of many terms. Of course, the method of choice for minimization is the gradient descent. Okay, but these are non-convex problems. Usually gradient descent, you get stuck into local minimum, and you're dead there. All right? You do not get to the global minimum. So the method of choice in machine learning is so-called stochastic gradient descent, where at each iteration, you select a few loss functions randomly and do gradient descent only for those few functions, instead of do a summation of many loss functions. So there are two benefits for this. One is, of course, this randomness adds some noise, which give you a probability to escape from local minimum. The second, of course, you save the cost because you don't take gradient of all 1 million functions. Well, if you come from kinetic community, there's also this so-called direct simulation Monte Carlo pioneered by Birds, where basically you, instead of solving Boltzmann, you simulate the particle interactions, collisions. You solve particle collisions directly, all right, by randomly select two particles, for example, let them collide and certify conservation laws and so on. So that's called direct simulation Monte Carlo. It's the most popular method actually to solve Boltzmann, which is very high dimension. And more recently, this idea has been adopted to solve mean field equations for flocking models using random binary interaction. For example, the work of L.B. Prasky and later Jose Carrillo also joined the effort. Sorry. Okay, now I have a little theorem which tries to convince you that this method works. All right. So we make few assumptions, very basic assumptions. For example, remember we have this external potential V. So assume that is strongly convex, all right? And what does it mean strongly? It basically has to be more convex than this x squared. Okay. Oh, okay. And then you also assume that the derivative has some growth, x to the power q. And this interacting potential, assume it's bounded. Lipschitz with Lipschitz constant L and has bounded second order derivative. We also assume that this R here is bigger than 2 times L. Basically, what this condition means is that this dynamic system, if you don't have this Brownian motion term, then this dynamic system actually is a contraction, right? So if you start with two sets of initial data, you get a solution xi and yi, then the L2 distance time derivative is bounded by itself, time this constant. Well, under this condition, of course, this constant is negative, so this guy would decay exponentially, this distance. But of course, if you add a Brownian motion term, then you have a non-trivial global equilibrium, for example, a Gibbs distribution and so on. All right, so here are very simple notations. Analytic solution is xi, numeric solution is xi tilde. We assume all the particles are indistinguishable, all right? You take the difference between these two, numeric solution and analytic solution. These are vectors. You take L2 norm, take expected value, square root, so that's my norm. That's my error. Well, it turns out if you have the error for this quantity, then it implies error for this y2 distance. Okay. So here's a little theorem. So suppose we have these assumptions on the potential. Then basically this error is bounded by square root of time step. So why square root? Essentially here we have a Monte Carlo in time. Okay. Because at each time step, I'm not doing the right thing. I only interact with a few particles, but the cumulative cost is the same. So it's square root of time step, but the key issue here is this constant. All right, this constant actually is independent of n. So that's very crucial. So because this is independent of n, essentially, we can choose time step based on our tolerance requirement. Has nothing to do with n. Okay? So indeed, our cost has been reduced by n, does not take n times longer to finish this process. Okay? So that's basically error analysis. And of course, once you have this error, then you have same error for the 1 and 2 distance between the first marginal of analytic particle system and this numerical random batch particle system. Basically, it gets same error estimate. Okay. And why this is true? So these are some heuristics. Basically, what we did is we replaced this order n summation by order p summation average. Of course, this difference is not 0, all right? But this is basically the truncation error. However, it's easy to prove that if this x is independent of the permutation, the expected value of this is 0. Okay? So I'm taking small samples, I take average. The expected value is 0. That's actually, that's how you do if you want to predict who will win the next US election. You don't call 300 million Americans, ask everybody who are going to vote for. What you do is just randomly select a few samples. So that's what they do this survey, this poll, exit polls. You select a few, it has to be unbiased selection, all right? You cannot only poll people in California or in New York City. You have to randomly, unbiased select, then a small sample average give the same expected value, essentially, all right? Not without error, there's a margin of error, but it's small. So you see this expected value is 0, which means if you do truncation analysis, the leading order truncation has the expected value 0, then you go to the next order, which gives you this square root of t. It's a very simple element. You can also compute the variance of this difference. The variance actually it is depends on this lambda, which of course depends on kernel. But this is order 1 quantity because you add n term divided by n. So this is order 1. Now the coefficient is interesting. It shows how the size of each group affect your variance. So it's a reciprocal of this each size, the p. So as you increase each small subgroup p, you reduce the variance. Of course, if p is n, which means you are doing the original summation, there's no variance. All right? So this shows you how the variance, because this is a Monte Carlo method, so the variance depends on the size of each batches. All right? So essentially what we proved here, and for example, if you use the empirical measure, this is numerical empirical measure when tau goes to 0, converges with order of square root of tau to this analytic empirical measure. But of course, if n is very large, one can pass to this mean field limit, which is the Fock-Planck equation. And the error from here to there is usually 1 over square root of n. Okay? So therefore, our method is not only a numerical method for this particle system. When n is very large, you can view it as a numerical particle method to solve this Fock-Planck equation. All right? So it does two things. That's what is usually called asymptotic preserving. So you have a scheme which essentially works for all range of n. Okay? When n is very large, basically you are solving effectively this Fock-Planck equation, and it's not very large, or intermediate large. You can view it as a numerical method for the particle systems. So that's the case if you have this trapping potential, and you have this constant actually is independent of t. If you don't have trapping potential, if I don't assume I have this external potential, which is a strong convex, you can still get the same error estimate, except this constant may depend on t. In this case, if you do ground wave inequality, you get an error which depends on t. But if you solve the original ODE, you get a constant like that anyway, okay, if it's not contraction map. So we have a trial. So this theory has some assumptions on the regularity of the kernels, but in practice, actually, we tried all different applications. We saw different kind of kernels. This kernel, in this example, this assumption on the kernel is not satisfied, but numerically they works. It comes from all different applications. I just give a few of them. One is so-called Dyson-Brownian motion, and Dyson actually just died a few days ago. So this slide is dedicated to him. And Dyson-Brownian, basically, if you want to solve eigenvalue of a random matrix, a Hermite-valued Ornstein-Uhlenbeck process, then actually this eigenvalue, J's eigenvalue of this random matrix solves this so-called Dyson-Brownian motion, this particle system. So this is like this is like external potential with a harmonic oscillator potential. So this is interacting potential and some Brownian motion here. As you can see here, the interacting potential is very singular. So it does not satisfy the assumption of my theorem. All right, because when lambda j is lambda j, lambda k is too close, it's very singular. And this particle system actually has a mean field limit. If I send n to infinity, and then this empirical measure actually solves this PDE, where this pi is where the h is a Hilbert transform. And this PD actually, if beta equals 1, has an analytic solution, which is given here in time. And if you take n to infinity, is this function, which is half over the circle. This is called a semicircle law. That's the empirical measure. So what we did, we have these two versions of random batch, all right? And we just do that. We choose p equals 2. So each group has 2 particles. Each particle interacts with 1 more. And the solid lines analytic solution, this is initial data, and some intermediate transient solution, and this is a global equilibrium in random measure. So as you can see, this our particle systems follow this curve closely with some noise, of course, because this is a random method. So this is the one without this random permutation. This is the one with replacement. Okay? So there are two different versions, but they give roughly the same, have the same behavior numerically. And this second example is a very classical physics problem, this so-called Thomson's problem, where you put like n electrons on a sphere, and they interact through Coulomb interactions. You ask, what is the global equilibrium of this system? Okay, and actually, when n is small, the number of electrons, there are analytic solutions up to, I think, up to n equals 12. There are few n's where you can solve this problem analytically. But here, what is interesting is if n is very large, what is the equilibrium distribution? All right, it turns out that equilibrium distribution is the minimizer of this energy, where this kernel is very singular because here is the Coulomb interaction. So you try to minimize this energy. One can solve this minimization problem by evolving actually a particle system, which is a particle system on sphere. So here it's a particle interact with Coulomb force. This F is a Coulomb force. Then you project that onto a sphere, and then you have this Brownian motion on sphere. Okay? So that's how one can solve this problem by evolving this dynamic system. So the way we do is if you use p equals 2, actually, remember this Coulomb interaction, if you do Coulomb with one more guy, you can do that analytically. You can find this ODE, you can solve analytically. So that's what we do. We solve analytically, then we project, because these xi are vectors. You solve it analytically, then you divide by each vector by its length, then it becomes a unit vector, so they are on unit sphere. So our method just has 2 steps. Okay? You evolve this one particle Coulomb interaction, then you project it to the unit sphere by dividing by its magnitude. And so this is you see the decay of the energy. This here, the particle is 60 particles, this is 800 particles. You see the decay of energy. And actually, the invariant measure is a uniform distribution for this problem. And you do see that these particles are kind of uniform distributed on the sphere. Okay. And then you can do also this mean field game. Well, that's a model by Degong, Liu, and Ringhofer, where you basically solve these coupled second-order particle systems. Why I use this example to show you that actually it works for long-range interaction. Coulomb is already long-range, okay, but it's still decaying distance. This example where actually the interaction grow in distance, so this phi. Actually, we can choose phi is 1/2 y squared. So it means if you take gradient phi, it's the length of y. So here the interaction grow linearly in distance, which is a very long range. Another difference here is actually it's a multiplicative noise. Okay, for our theorem, it works for additive noise, but numerically, it also works for multiplicative noise. So that's the distinctive feature of this example, multiplicative noise and long-range interaction. So it turns out the solution, actually, we can get it right. I mean, this Solid line is that you do the original computation, use whatever standard method, and this random batch method give you the right solutions. And we can also do opinion dynamics and so on. Maybe I just skip a few more examples. All right, so that's the story about the classical particles. Any questions so far? And then more recently, actually, with Francois and the theory, we thought about the question, how about quantum? And after I give talks, people keep asking me about quantum particles. So we give it a try, all right? So this is the n-body Schrodinger equation. Well, H is the Hamiltonian, which has two parts. This is kinetic energy, that's the potential energy. All right. So here, you can see the n particles. They interact physically through Coulomb potential. And so, of course, we know that the difficulty of the problem is that usually the n is very large, so this is the curse of dimensionality. And then, of course, this here, the summation term, here's all the n square summation. All right, you see this summation with double indices, all the n square summation. So the main challenge in quantum, if you can solve this, is called first principle simulation. If you can do that, you basically understand everything about matters, about physics, essentially. But we know the difficulty here is that first n is large, second h bar is small. Okay. So of course, it's a very natural thing. One can do this interaction by random batch. Essentially, just pick two particles, and you replace this order n. Each particle will interact with one more particle. And you do this random batch. You randomly arrange them pairwise, okay? And then, of course, you can reduce the cost of this term from order n squared. This is order n squared summation to order n. You can do that. But however, the question is that correct? Does that give you the right physics? And it turns out this problem is more challenge than the classical particle because here, if you look at this right-hand side, here we have order n squared summation, but it's only divided by n. In the classical particle, it's all the n-term summation divided by n, so that's order 1. But here is order n squared divided by order n. So if you make a mistake here, because this whole operator, also this operator, you have a Laplacian for n particles. So if you make an error for each term, the error will be amplified by order of n, all right? Because this is order n operator. So if you do a crude error analysis, you get an error which is multiplied by n, and also you have this h bar in front of time derivative. So the error is multiplied by n divided by h bar. Cannot be worse than that. I mean, this large parameter all appear in the best place. The error is, whatever error you make, amplified by n and divided by h bar. So it's terrible, looks terrible. So for example, if you just do pairwise interactions, and basically if we introduce this random projection operator, basically if two particles are in the same group, this thing is 1, otherwise 0. So you replace this original n-body interaction by this pairwise random interaction with this operator over here. And this is basically mathematical settings. Basically, we work on this L2 space with the density operator. And if you use density operator, then the density operator solve this n-body von Neumann equation, all right? Where this bracket stands for this commutator. And of course, the analytic solution for the original Schrodinger with the Schrodinger Hamiltonian, you can solve it analytically with this notation, or operator notation. While solution of von Neumann, likewise, had also analytic solution if you given the initial density operator. So you evolve forward and backward by this Hamiltonian. Of course, with the random batch, if you do random batch, we replace this Hamiltonian by this random batch one. Then you have this random batch von Neumann, which I put the solution I call R tilde. Okay? So the difficulty of this problem is that if you look at the error between this random batch density operator and the original density operator. The first question is, what is the right measure for error? A classical measure for error, for example, that has been used for studying mean field limit is the trace norm. But if you do trace norm, actually you do not find the error that's independent of n. It depends on n. The second question is, actually, if you do this, you do not expect to get the density function right. The per psi, you're not going to get it right. Okay, that's too much to ask for. So what can you get right? So you consider what is the right quantity of interest. Okay, what are the physical quantities this method give a good approximation. So it turns out is this so-called reduced density operator. I will define in a second, all right? Another difficulty is that actually we know if you take the mean field limit, one important assumption is that this density operator is symmetric with all the variables, all these x. So if you interchange the xi with xj, it does not change the solution. However, this random batch destroys that because you only interact with the selected guy, not the uniform with all the other guys equally. All right, so you destroy that. So essentially all these classical tools doesn't work here. Okay. So those are all these difficulties. So it's a very challenging problem. It turns out the quantum of interest we consider is so-called a one-body reduced density operator. I mean, so this is basically the first marginal. Okay, you integrate out all the variables except x1 and y1. But because of the loss of symmetry, actually what we need is we have to take, you have this integrate all the variable except the ith variable, but that's not symmetric. So you have to add all these totally n first marginals, take average. Take this averaged first marginal, all right? So that's the quantity of interest. And then, of course, if you find that if you use a standard trace norm, actually, what you typically end up is the error estimate like this. That's exactly what I mentioned earlier. So well, this is a weak norm, so you get all this is a time accuracy, the order delta t, but you multiply by n divided by h bar, which of course n is large, h bar is small. It's terrible, looks terrible. Okay. So here the key contribution in this work is that one has to introduce a new metric for the density operator, which is given here. It looks complicated. It's a trace norm between these two density operators. Is this distance. To motivate a little bit, actually, it's something of an analog or extension of this Monge-Kontorovich or Weisel distance of exponent 1, which is given here. Except in the classical Monge-Kontorovich distance, you have this constraint, which only involves the first order commutator. But here, we need a second order commutator here. That's really because of this random batch business, all right? You have to also control this second order commutator. So our main result is that this distance between the first marginal of this analytic density operator and this numerical one, the expected value numerical one, is bounded by essentially order delta t. And if you look at all these other things, there's no h, there's no n, no h bar. So the error estimate is independent of n and independent of h bar. Okay? And the proof is very much involved. It really takes people like Francois and Thierry to tackle this problem. It's very, you need several main ideas, which I will just sketch here. First is that if you if you estimate this commutator between the function and the operator, you have to, then usually it doesn't work, and you do not get a nice n and h bar independence. I mean, you have to, by doing Fourier, put in the Fourier space, you convert the commutation of this commutator into the commutator between this x component, x variable, and this operator. Okay. Second, you have to define, when you define this average first marginal, that's what is here. And one realizes that if you do a commutator between this x, called it x variable instead of general function, with this averaged first marginal operator, and then every terms are 0 except when this m equals k. So you kill m minus 1 term, you only one term survive. That's how you get rid of this capital N business in the air. Okay? And then, of course, when you define this first order marginal, the definition of A is very crucial. It turns out if you take A to be the Y operator, then all this commutator, which looks order 1 in this term, you have term, if you do error analysis, the truncation error has term like this, which is order n summation, which looks like order 1 term, even with n. However, if you do this commutator, becomes a commutator between x and this Y operator, then this commutator is order h. So that's how we get rid of this h business in the denominator. Okay? And so this helps you. That's how we get rid of the h bar. So similarly, you have to do error estimate for second order commutator. This is an example of a first order commutator. It turns out a second order commutator because you get this h bar square, which kills order of h bar square. So those are basically the key ideas. So it's rather involved proof. So to conclude this part of a random batch, essentially we know that the Newton equation and the Schrodinger equation, for m-particle systems, are two of the most fundamental equations in physics, right, with many, many applications. And we proposed a very simple random batch method to reduce the computational cost of n-body interaction from n squared, order n squared to order n. And we have error analysis. In the classical particle system, the error is independent of n, while for the quantum one, if you do this average first marginal, you get the error estimate uniformly in n and h bar. Of course, you can ask a lot of other questions. For example, if you take here, we only have the error of the random batch. Okay, if you do time discretization, and also the conversion toward global equilibrium, so you have error, time-dependent error analysis, but sometimes you are interested in the long-time behavior, and that's the conversion to the global equilibrium. And of course, theoretic justification of mean field limits, or people ask, can you have a weaker regularity for the potential, and so on. So there are lots of questions one can ask. So before I jump to the next topic, any questions so far? Okay, well, the next topic looks like a completely different area, but it's related, all right? The next topic is about the non-convex optimization, but we're going to use interacting particle systems. So let me come back to this machine learning problem. I mentioned the machine learning earlier. And so nowadays, for example, if you do a deep neural network, that seems to be very powerful things for a lot of things. And what you need to do is you have this set of data, which is given xi hat, the yi hat, which is called a test data. And they're trying to find an approximation, like a neural network approximation f, which is some kind of approximation, such that then this numerically fitted approximation, the distance, some distance is called loss function between this numerically fitted solution and your target solution. This distance is minimized, all right? So typically, this n is very large, millions or billions. And you basically want to find the global minimum of this function, the loss function. And this function typically is non-convex. And we all know non-convex optimization is NP hard problem. Okay? And of course, as I mentioned earlier, the most popular method used for machine learning is the stochastic gradient descent method. But of course, by definition, you need to take gradient. You have to take gradient. Okay, with this method, you have to take gradient. So of course, in the case when the function does not have the good regularity, which does not allow you to take gradient, sometimes you only have data where you even don't have functions. So therefore, it seems to be, you try to find an alternative method which does not need gradient. Seems to be a reasonable choice, right? So that's what we are going to talk about, gradient-free numerical method for global non-convex optimization. So of course, there's already big industry for this. Actually started from 70s or 80s. A lot of people are doing this, using so-called simulated annealings, genetic algorithms, they're all kind of a method. The method we're going to talk about actually fit into this so-called swarming intelligence, where you consider a collective, large number of agents. Okay, these agents are inspired by insects, animals. And they select basically agents that interact with each other in some intelligent way. And individually, they work they move in some random fashion, but collectively, this community of agents are quite smart, quite intelligent. So it's called swarming intelligence. So we all know this AI stands for artificial intelligence. Here I'm talking about animal intelligence. My AI is animal intelligence. It turns out these animals are quite intelligent, all right? It's more smarter than what we think. So here are a few examples. For example, particle swarming optimization. If you consider, these are some of the examples of this approach. And the colony optimization and artificial bee colony optimization. And here is a little animation. Basically, you have these are contours of functions you want to find global minimum. So you have these particles that kind of uniform distributed initially. Then you design mechanisms such that eventually they all converge to the same point, which are your global minimum. Okay. So actually, this business has a name. It's called a meta-heuristics because it's a heuristic you learn from these insects, all right? But this turns out this community does not have a very good reputation. And people, if you write paper on this business, it's very easy to get rejected by mainstream community. The reason actually, I stole this from Wikipedia, all right? This is what this review article says. Basically, most literature on meta-heuristics is experimental in nature. And these results are empiricals, lack of concept elaborations, poor experiment, and so on, all right? Well, of course, today we will develop actually such a swarm intelligence method, which we have some theory, okay? We can prove under certain conditions, this particle system will converge to global minimum for general non-convex high-dimensional functions, all right? We do have some little theory. So our starting point is so-called consensus-based optimizations, these two papers. These are the group in Kaiserslautern. And later, Jose Correa also joined the effort. So it's a very simple particle system, all right? So here we consider m particles. And the first part is just almost trivial. It's kind of a relaxation. So all these particles eventually relax to this guy, this kind of average, okay? Then they do some Brownian motion. Depending on the distance between each particle and this average, they do some Brownian motion. Okay. And the key, of course, is choice average. So this is how we design this community of this particle. You design a way such that they behave in an intelligent way that you hope for. So the definition of this average actually is the weighted average of this Gibbs measure-like weight. So essentially, this particle xj multiplied by this weight, which is e to the minus beta L. L is the function you find a minimum, all right? That's your target objective function. Beta is some positive constant, which is assumed to be large. So this term looks like Gibbs measure, where L looks like energy. Beta is like 1 over temperature. So from here, the way it is designed, I mean, if you have smaller value of L, then the weight is larger. So the particles with a smaller value of L, which is what you like, you give them a higher, more award. So this is the awarding society. You give an award to the good guys who behave nicely. You give that more weight. So that's how this society works, all right? That's how the society should be working. So that's how this average is determined. And actually, why this kind of average? Actually, it has to do with this so-called Laplace principle, which is an important theory from large deviation theory. So essentially, this the Laplace principle says the following. If you have x is a random variable, so rho is a probability measure. Suppose this support of a probability measure contains this x star, which is global minimum of L. Then this integral of e to the minus beta L, d rho, you take a log divided by beta. When beta goes to infinity, the limit is exactly the global minimum of L. So that's the Laplace principle. So with this Laplace principle, then I can easily show that if n goes to infinity, this guy essentially will concentrate on this x star, which is the global minimum. All right. So that's how this society is organized. So actually, in their paper, they can prove that for sufficient beta, large beta, and this particle form a consensus. Eventually, particle all converge to the average, and it's exponentially fast. But of course, these parameters, this drift rate and this strength of a Brownian motion has to satisfy this condition for convergence to consensus. 2 lambda has to be bigger than sigma squared times d, where d actually is the dimension of x. So this method actually works quite well if d is not very, very large. But when d is large, I mean, this is terrible conditions because the drift rate is very high. By the time you're very close to the global minimum, all of a sudden you are drift away. So the method does not work very well for high dimension problem. So we were together with Jose and Lei again, and Yuhua Zhu, who was my last student from Wisconsin. She's now a postdoc at Stanford. So actually, we did a very little modification of this model. So the way we did, if you remember this Brownian motion term, which has this bar here, that's the length of this vector. So here what they do is you have isotropic Brownian motion. In every component, you add the same amount of Brownian motion, okay? What we did is just we remove this bar. You do this component-wise. So for each component, this is a unit vector in the k's direction. You just use the k's component of this vector. So we do a component-wise Brownian motion. Actually, this time is exactly geometric Brownian motion. Well, do other tricks, because there's these summations here where you do this random batch idea. Okay, instead of adding all these functions, which is computing very costly, we add a random small batch. And all this average, that involves the summation of many terms. We select the mini batch, random mini batch, where you do all those tricks also. So why this is better? Okay, it's a very simple example. So suppose this average is constant. Suppose this average is constant. Then actually you can solve this problem, this stochastic PD by hand, analytically. Right? In the original model, then basically this is a deviation. So x minus this average, expected of this square time difference. The drift term actually gives you this, which gives you the exponential decay of x toward its average, right? That's the drift term. While Brownian motion term actually give you summation of all the variable, all the component of x up to d dimension of this quantity. But you have to add all these terms by the d terms of this. That's why you have this d here. So for this to decay, x to converge to a, you need this constant to be negative. So 2 lambda is bigger than d times sigma squared. That's where this comes from. However, if you get rid of this bar, then same exercise shows you that now I have this component, each component-wise expected value. Now if you add d terms, it's exactly this vector, no more d. So therefore, this guy decays as long as 2 lambda is bigger than d squared. So therefore, now our algorithm works under the condition that does not depend on dimension, which allow this model to be better performed for higher dimensional problem. Okay, very simple modification. Well, we have some theory. There are 2 theories. The first theory is you take a mean field limit, send n to infinity. Then the original particle system becomes this stochastic ODE, where this drift term is between x and the average. Because if you send n to infinity, now these summations become this expected value of this weighted x times this Gibbs measure divided by the normalization factor. And of course, this Brownian motion term is just the component-wise. This is a geometric Brownian motion. And if you use the empirical measure, you have this Fock-Planck equation. All right, so this is the drift rate, and this is the Brownian motion term. So for this mean field limit, actually, if you assume that L is strictly positive, and you also assume some boundedness of a second derivative L, essentially. This is Hessian matrix, spectral radius is bounded. Then you check this variance of x toward its expected value. And you can prove that under this condition, so this is condition on the parameter, and the initial data also, you have some condition on the initial data. And of course, it looks complicated, but you look carefully, d is not there. So the dimension parameter is not there. Okay. Then you can prove this expected value is converges to 0 exponentially fast. Okay. And of course, the question is, where does it converge to? And actually, this is the L estimate. All right. Right. So basically, it converges to this guy x tilde, where the L value at x tilde is bounded by this global minimum, plus these terms, which are L terms. That's essentially 1 over beta. Remember, beta is 1 over temperature. We choose beta to be large. And then here we have this is constant independent of d, but you have this log b, which is not a big deal when b is beta large. But I mean, the only issue here is you have this d here. So essentially, looks like this method works if beta is larger than d. You get a nice end. Basically, your converged solution is in a small neighborhood of this global minimum. Okay? And that gives you basically the distance from the global minimum. So the convergence itself does not depend on dimension. However, the L, of course, does have this linear dependence on dimension. Okay? So this method works for moderately high dimension, not for extremely high dimension, at least the theory. I mean, of course, these are sufficient conditions. So that's what the another constraint is that you need good initial data. Remember, I have to assume that it's initial support of the initial gas. The law has to contain global minimum. So remember, this average is this good guy, right? You try to learn from, and you need this good guy in your community to learn from. I mean, if there's no good guy here, nobody to learn from. You're not approach to. I mean, all particle will not become a good guy. So you need a good role model in this community. And we also have with Song Yi-ha and so and his postdoc Kim. We also have a conversation not for the mean field limit, but for particle itself. All right. So what we have is we just work on the particle system. We can prove that particle I and particle j distance when t goes to infinity is 0, and the probability of the distance bigger than epsilon when t goes to infinity is 0 for almost every epsilon, which means all these particles will convert toward each other. And the reason why before in the work of Jose and so on, they always go to mean field limit is that they did not use the right norm for this business. All right, they use essentially L2 norm, which is then because ground inequality, you get the exponential decay term, growing term for the particle. That's why they go to a mean field limit. In our paper with Song Yi-ha, actually we use the diameter, which is exactly basically the L1 distance between different particles. So you work on the diameter, then you get this decay estimate. So this is what we get. For example, we have various results, but this is one example. So if you take, for example, this Euler approximation, this SDE we use forward Euler method, all right? And you do exactly forward Euler, then what we can prove under this condition, you see this condition does not depend on dimension, all right? And this is a step size because the h is like a time step. You have this stability condition like CFL condition. So under these conditions, particle xi and particle xj and the expected value of that actually will decay from the initial distance, will decay with this rate. Okay. And then, of course, if initially you take IID or under the same conditions, this is a condition on the initial data, which actually looks complicated, but it means basically initially you have to be close. You need a good initial guess for this to work. Very much like if you do Newton iteration to find the root. You need a good initial guess, same here. Then we can prove essentially the same error estimate, all right? So if you have to assume if the support law of the initial distribution contain this global minimum, then this particle system will converge exponentially to this x tilde, which is in this neighborhood of your global minimum, where again this area is the same. So some numeric examples. So this is functions of 20 dimension, and you can see it's highly oscillatory. This is a global minimum. This is a one-dimensional plot of these 20-dimensional functions, all right? So this is global minimum. There are a lot of local minimum nearby. So if you use the deterministic method, you get stuck here. That's it, all right? So these are if you use this Kaiser-Slautern group method, and when D is 20 dimension, actually the success rate is not very high. I mean, and this number of particles from 50 is like 1/3 of a success rate. Well, remember that stochastic optimization does not guarantee every time you run it, you are successful, okay? A lot of time you don't succeed. That's the feature of a stochastic optimization. So you only compare the successful rate. So this is a successful rate. So if A is 15, their method is 30%, 34%. If 200 particles, 60%. Well, in our algorithm, we just get rid of this bar. Then essentially, for same parameters, essentially, we most time it's correct, 98% to 99%. And this is a very standard test for machine learning, for image processing problem called administered data. So here, usually in machine learning, you use deep neural network. Here, I just use a single shallow neural network, just 2 layers, all right? So this dimensional problem where you have input data, which is a vector of 700 dimensions, which corresponds to the grayscale of each pixel, all right? So here's a typical neural network. So you have this linear combination. So x hat is your test data. It's a linear combination of x. Then you do what is called activation function, which is in this case so-called a rectified linear unit, which is basically this function of x is just a positive part of x. Okay, it's positive part of x. So A is the activation function. Here we choose it to be this average. And this is essentially its optimization problem. It's non-convex, all right? It's actually this variable is 7,000 dimension. Okay, and here is the loss function. That's how you try to minimize these loss functions here. So here, these are our parameters. Basically, we just use 100 particles with different choice of a random batch. So we use 10,000 training data, and then you compare. What the way the machine learning does is you find a neural network works based on the training data. Then you use test data to see whether you get it right. All right, it's very much like you show 1,000 pictures of Francois. The machine recognizes, okay, this is Francois. Then you get a different Francois without glass, whether you can still recognize Francois, all right? So this is the success rate on the test data, 10,000 test data. And if this parameter, you just use 100 particles, we get about 80% correct. Okay, 80% correct for all different parameters. And if you increase the parameters, if you use 1,000 particles, then we get almost 90%, which is almost the same as the best stochastic gradient descent can give you. Okay, over 1,000 simulations. Okay, basically I'm finished. So of course this is more works needed to be done. And first, at least it seems to me, this particle system is a very natural way to solve a global minimization because you mobilize a lot of particles. Imagine you are in the mountains, you're trying to find the best path to go down. If you just one guy is searching around, it takes forever. If you have many guys who try different particles, then talk to each other. Okay, I find the best way here. Everybody come here. That's a better way to do global minimization if you have very complicated landscape. So I think it's a very similar. I think it's has some advantage of this intelligent community than individuals. Okay, if you do gradient descent, you have just individuals which look around. It takes a long time. Same for similar annealing. But this here will have a community. We mobilize the community, and you organize the community in some intelligent way, which allows you to achieve your goal in a more efficient way, faster way. Of course, there are a lot of interesting analysis that needs to be done, right? I mean, for example, full discrete system, also this random batch method for this, we haven't done any analysis. Also this convergence, we have sufficient conditions, but they are not necessary. We tried some other parameters which does not satisfy the conditions, they still work sometimes. And also another important convergence analysis, we do not have convergence on n. So what's the best choice of n so far is not known. Also, the initial data is very crucial. That's probably the most disadvantage of the method. You need good initial data. Okay. And of course, there are a lot of other interesting questions in field limit and more tests and errors analysis and more generalized optimization problem. Okay. So for that, I stop. Thank you very much.